In this lesson, we will discuss primality testing and methods for factoring large integers. So recall in the RSA algorithm, the security depended on the fact that it's very hard and takes a long time to factor large integers. So in this lesson, we will discuss some of the techniques that are used to factor large integers. The first result that we'll discuss is the basis for the best current method for factoring large integers. So we're going to call this the basic factoring principle, and we'll refer to this later. So let n be an integer. And suppose there exist integers x and y, such that x squared is congruent to y squared mod n. But x is not congruent to plus or minus y mod n. Then we can conclude that n must be composite, moreover, we can find a non-trivial factor. So the greatest common divisor of x minus y and n is a non-trivial factor of n. This basic factoring principle is the basis for the best current factorization methods. So let's get the proof of this result. Let d be the greatest common divisor of x minus y and n. So we will show that d can't equal n and d can't equal 1, and therefore d is a non-trivial factor of n. So for a contradiction, let's first assume that d equals n. Then n must divide x minus y, and I can write x minus y as an integer times n. So x minus y equals n times k for some integer k. Then adding y to both sides of this equation, we see that x equals y plus nk, and therefore x is congruent to y mod n. This is a contradiction from our original assumptions. because we assume that x is not congruent to plus or minus y mod n. Therefore, d does not equal n. Now suppose that d equals 1. In other words, x minus y and n are relatively prime. Recall Euclid's lemma, which states that if A divides a product BC, and A is relatively prime to B, then A must divide C. Well, since x squared is congruent to y squared mod n by assumption, we see that n divides x squared minus y squared, which I can write as the product x plus y times x minus y. So n divides the product x plus y times x minus y, but we're assuming that n is relatively prime to x minus y. So since the GCD of x minus y and n, which we define as d, is 1, we know that n must divide x plus y by Euclid's lemma. But then, if n divides x plus y, then x plus y is a multiple of n, and x would therefore be congruent to negative y mod n. Again, a contradiction. Since d does not equal n, and d does not equal 1, and d is a factor of n, d must be a non-trivial factor of n. Now that we've established one of the basic principles used to factor large integers, let's talk about primality testing. So primality testing is the process of determining whether an integer is prime. So you might think that determining if an integer is prime and factoring an integer are about the same process, but it turns out that it's actually much easier to prove that an integer is composite than it is to actually factor that integer. So next we'll discuss a primality test, which actually would be better called a compositeness test, since it gives a completely certain answer only in the case when n is composite. But first I want to recall Fermat's little theorem. So this is just a special case of Euler's theorem when the modulus is prime. Recall that it says that if P is prime and P does not divide A, then A to the P minus 1 is congruent to 1 mod P. So Fermat's little theorem is the basis for the following primality test called the Fermat primality test. Let n be an integer greater than 1, and choose a random integer a between 1 and n minus 1. Then if a raised to the power n minus 1 is not congruent to 1 mod n, then n is composite. So in this case, Fermat's little theorem states that if n was prime, then a to the n minus 1 would have to be congruent to 1 mod n. So since a to the n minus 1 is not congruent to 1, n must be composite. Now if you compute a to the power n minus 1 and it actually is congruent to 1 mod n, then n is probably prime. So note the word probably. So we see that this test can definitely confirm that n is composite, but only tell you that n is probably prime in the case when a to the n minus 1 is congruent to 1 mod n. So let's see an example of the Fermat primality test and the basic factoring principle. So I want to show that 55 is composite. I'm going to show this two different ways. First, by the Fermat primality test. So we need to compute 2 to the power 54 mod 55. So if you tried to just plug in 2 to the power 54 on a calculator, this number might be so large that you won't be able to reduce mod 55. But we can evaluate these modular exponents by doing successive squaring of the base and then reducing mod 55 each time. So for example, let's start with 2 to the 6th power. 2 to the 6 is 64, which is 9 mod 55. So then I can compute 2 to the power 12, because 2 to the 6th is 9. This is congruent to 9 squared, or 81, which reduces to 26 mod 55. Then 2 to the power 24 would be congruent to 26 squared. This is 676. And when I reduce mod 55, I get 16. 2 to the power 48 is 16 squared, which equals 256. And when I reduce mod 55, I get 36. So then 2 to the power 54, that just equals 2 to the power 48 times 2 to the power 6. Well, 2 to the power 48 we know is congruent to 36, and 2 to the power 6 is congruent to 9, which equals 324. And when I reduce mod 55, this equals 49, and this is not congruent to 1 mod 55. Therefore, by the Fermat primality test, 55 can't be prime. But notice that we still haven't actually factored 55. So now I want to use the basic factoring principle. So notice that 8 squared, which is 64, reduces to 9 mod 55, but 9 is the same as 3 squared. And notice that 8 is not congruent to plus or minus 3 mod 55. So the basic factoring principle tells me that 55 is composite, but it also gives us a non-trivial factor. So the non-trivial factor would be the GCD of 8 minus 3 and 55, which is the greatest common divisor of 5 and 55, which equals 5. And this is a non-trivial factor. Now let's begin to talk about techniques for factoring large integers. So recall that if n is composite, then n must have a prime factor p, which is less than or equal to square root of n. So why don't we just look at all the primes less than or equal to square root of n, and to check to see if n is composite. Well, this is going to take way too much time, and this is a very, very slow process for large n. So it would take too long to try to factor n by dividing by every prime that's less than square root of n. So just to illustrate this, suppose that n is a number that has 200 digits. Then square root of n has approximately 100 digits. So how many primes are less than or equal to square root of n? One of the biggest achievements of number theory is the prime number theorem, and it involves the prime counting function, which we're going to call pi of x. So the prime counting function pi of x counts the number of primes less than or equal to x. So what we want to do is find pi of square root of n. Okay, remember n is a very large integer, so we want to know how many primes are less than square root of n. Well, the prime number theorem states that the number of primes less than x, less than or equal to x, so that is pi of x, is approximately equal to x divided by the natural log of x when x is very large. So by using the prime number theorem, we can approximate the number of primes less than or equal to square root of n. So the number of primes less than or equal to square root of n. And let's just assume that n is about 10 to the power 100. By the prime number theorem, this is approximately 10 to the power 100 divided by the natural log of 10 to the power 100. And this is approximately equal to 4 times 10 to the power 97. So for an integer n, which has 200 digits, there's approximately 4 times 10 to the power 97 prime numbers that we would have to check. So how long will this take? Well, as of July 2014, the fastest supercomputer would not be able to check each one of these primes in our lifetime. So as of July 2014, the fastest supercomputer has a speed of 33.86 petaflops, which means it can compute 33.86 times 10 to the 15th power operations per second. So suppose that each one of these operations could check one prime to see if it's a factor of n. So suppose this computer could check one prime for each operation. And in order to check each one of the primes less than square root of n, so it would take approximately 4 times 10 to the 97 divided by 33.86 times 10 to the 15th seconds. So this would be 1.18 times 10 to the power 81 seconds, which would equal 3.7 times 10 to the power 73 years. So it'll take this long to check all the primes less than or equal to square root of n. So even if computing power increases in the future, it still would be infeasible to check all the prime factors less than square root of n to determine if n is prime. So we need a better technique. So next we'll present a technique based on the basic factoring principle that is actually the second fastest method known for factoring large integers. It's called the quadratic sieve algorithm. So this is based on the basic factoring principle. So I'd like to take a moment to review the basic factoring principle. So if we can find integers x and y such that x squared is congruent to y squared mod n, but x is not congruent to plus or minus y mod n, then we can conclude that n is composite and we can find a non-trivial factor, which happens to be the greatest common divisor of x minus y and n. So this is the basis for the quadratic sieve algorithm. As I stated, this is the second fastest method known for factoring large integers. After the number one fastest method, which is called the general number field sieve. So I'm going to give a simplified example of the quadratic sieve algorithm. So in this example, suppose we want to factor the number n, which is 3837523. So there's going to be two phases of this algorithm: data collection and data processing. So there are two phases of this algorithm. Data collection and data processing. Let's begin with the data collection phase. So typically, the data collection phase involves connecting many computers via the internet in order to search for congruence relations mod n. So many processors are typically parallelized to produce congruence relations of squares of the form x squared is congruent to a product of small prime numbers mod n. So for example, suppose we obtain the following relations. So in these relations, the small primes make up a set called our factor base. So once again, these relations are often found over several months, maybe even years, using computers that are connected via the internet so they can be working together on this problem. Now let's go to the data processing phase. So each of the squares that were produced during the data collection phase is converted into a row of a matrix. And the matrix has entries that are the exponents of the primes in our factor base. So in our example, our factor base consists of primes less than 20. So then the matrix is again corresponding to the previous squared relations. Now once we have this matrix, we look for rows that we can add together to produce a vector with all even entries. Here are two examples. If we add the first row, the fifth row, and the sixth row of the matrix together, we get the vector 6, 0, 6, 0, 0, 2, 0, 2. And if we add the third row and the seventh row together, we get the vector 0, 0, 2, 2, 0, 4, 0, 0. So when we write out the corresponding factors, we obtain congruences of the form x squared congruent to y squared mod n. So if it happens that x is not congruent to plus or minus y mod n, then we can find a non-trivial factor. The GCD of x minus y and n is a non-trivial factor of n. So let's write out the corresponding factors of these two examples. In the first example, we get 9,398 times 8,077 times 3,397, the quantity squared, will be congruent to 2 cubed times 5 cubed times 13 times 19, the quantity squared. And when I multiply this out, we get 3590523 squared is congruent to 247000 squared. But in this case, we don't get a non-trivial factor of n because 3590523 is actually congruent to negative 24700 mod n. So let's look at the second example. From the second relation, we get 1,964 times 14,262, the quantity squared, will be congruent to 3 times 5 times 7 times 13 squared, the quantity squared. This gives 1147,907 squared is congruent to 17745, the quantity squared, mod n. Notice that 1147,907 is not congruent to plus or minus 17745 mod n. So therefore, the greatest common divisor of 1147,907 minus 17745 and n, which happens to be 1093, is a non-trivial factor of n. And therefore we can factor n. So the other non-trivial factor is n divided by 1093, which is 3,511. So these numbers are both prime, so we've completely factored the number n as 1093 times 3,511.